In circuit A, the bulbs are connected in a series. In circuit B, the bulbs are connected in parallel. Let's see how both circuits behave. The bulbs in circuit A are dimmer than the bulbs in circuit B. If a bulb is removed from each circuit, then the remaining two bulbs in circuit A stop glowing, but in circuit B they continue to glow. Can you explain why this should happen? The filament of the bulb is a resistor. Resistors are electrical devices that resist the flow of electric current. So, circuit A is an example of resistors connected in series, and circuit B is an example of resistors connected in parallel. Based on your observation of the bulb's behavior, can you explain how resistors connected in series differ from resistors connected in parallel? To understand the flow of current through these two resistors better, let us connect a voltmeter and an ammeter. Let us take the values of R1, R2 and R3 as 2, 4 and 6 ohms respectively. The potential difference across the first resistor will be V1. Similarly, the potential difference across the other resistors will be V2 and V3. The potential difference across the three resistors is equal to the sum of the potential difference across the individual resistors. By Ohm's law, V1 equals IR1, V2 equals IR2, V3 equals IR3. I is the amount of current and R is the resistance. How will you calculate the total resistance for this circuit? The total resistance of this circuit, IR, equals IR1 plus IR2 plus IR3. If the current flowing I is kept constant, then R equals R1 plus R2 plus R3. Thus, in a series connection, the total resistance and the total current flowing through the circuit are both distributed among the resistors attached. Also, if one resistor is removed or damaged, then it will cut off the flow of current. Let us do an activity. Consider a torch bulb whose resistance is 15 ohm and a resistor of 5 ohms. Both are connected to a 5-volt battery in a simple connection. Calculate the total resistance of this circuit, the current that passes through it, and the potential difference across the bulb and the resistor. First, we will calculate the total resistance in the circuit. The bulb's resistance is 15 ohm and the conductor's is 5 ohm. So, the total resistance is 20 ohms. The potential difference between the two terminals of the battery is 5 volt. By applying Ohm's law, we can calculate the current I flowing through the circuit. It will be 0.25 ampere. Now, by applying Ohm's law, we can calculate the potential difference across the bulb as 3.75 volts. And the potential difference across the resistor is 1.25 volt. If we calculate the total resistance in this circuit by applying the formula R equals V divided by I, we get the total resistance as 20 ohm. This 20 ohms is also the sum of the resistance of the bulb and the conductor. Let us now understand the arrangement of resistors connected in parallel. Let us take the values of the three resistors R1, R2 and R3 as 2, 4 and 6 ohms respectively. We have I equals V divided by R. By applying Ohm's law, we get these three equations for I1, I2 and I3. From this we can derive this equation also. Let us do an activity. Here, the three resistors R1, R2 and R3 are of 7 ohm, 14 ohm and 28 ohms respectively. They are connected to a battery of 10 volts. By using Ohm's law, we can calculate the current flowing through the first resistor. By applying the formula I1 equals V divided by R1, we get the amount of current passing through R1 as 1.4 ampere. Similarly, we can calculate the current passing through R2 is 0.7 ampere. Similarly, the current passing through R3 is 0.3 ampere. So, the total current in the circuit is 2.4 ampere. And the total resistance is 4 ohms. Note that the total resistance is lesser than the individual resistance because the resistors are connected in parallel.
You can feel the warmth when a bulb, a fan, or a computer is being used.
You know that these gadgets are the ones in which electrical energy is converted into some other form of energy. When you look at this fan, here electrical energy is converted into rotational motion. In the case of bulb, electrical energy is converted into light energy. But not all electrical energy is converted into light energy or motion. In devices like bulbs, the conversion part of the electrical energy into heat energy is undesirable. But there are instances where electrical energy converting into heat energy is absolutely desirable or necessary. If only part of the electrical energy gets converted into heat energy, then how much of electrical energy is required to generate a specified amount of heat energy? Or are there ways to ensure that such a device converts most of the electrical energy that it receives into heat energy? There are some devices that depend on a larger part of electric energy. In case of an electric fan, large form of electrical energy is used to do work as the fan blades keep rotating. Devices like clothes, iron, or heater have a resistive circuit. These devices have only resistors attached to the energy source. Therefore, the source energy is entirely converted into heat energy. Appliances like electric stove or clothes iron that get heated up have wires that are not severely impacted. Suppose an electric iron consumes energy at a rate of 840 watts when heating is at the maximum and its voltage is 220 volts. So first, let us find out the current I flowing by using the formula I equals P by V. By calculating, we get current I as 3.82 ampere. Now let's calculate the resistance R by using the formula R equals V by I. A current I is flowing through a resistor of resistance R. The potential difference across it is V, and T is the time during which a charge Q flows across. The work done in moving the charge Q through a potential difference V is VQ. So, the source must supply energy equal to VQ in time t. Also, the amount of heat produced in time t for current I will be H equals VIT. As we know by Ohm's law, V equals IR, we get heat produced as I square RT. This is Joule's law of heating. This law implies that heat produced in a resistor is directly proportional to the square of current for a given resistance, directly proportional to resistance for a given current, directly proportional to the time for which the current flows through the resistor. Joule's law finds many practical applications in devices of daily use. One of the most common is the electric fuse. The fuse is usually placed in series with the device. The fuses that are used for household purposes have ratings as 1 ampere, 2 ampere, 3 ampere, 5 ampere, 10 ampere. It is made of a material that will melt when the flow of current exceeds a specified level. What happens after this? The fuse wire gets overheated, melts, and the circuit is broken. This prevents fire and the appliance is protected. The smoke coming out of the building. A small electric spark may cause a major fire. When high current flows through the circuit, excessive heat is produced. It damages the electrical appliance and burns the wiring. Why should the heat be produced when excessive current flows? According to Joule's law, the amount of heat is directly proportional to current, resistance, and time of passage of current. We make use of this heating effect of current in the laundry iron, electric toaster, electric immersion heater, and fuses. A fuse is a safety device. It is a short wire made of an alloy of lead and tin. The alloy has a low melting point and low resistance. The thin wire is set in porcelain casing. The fuse is represented by a symbol as shown in the circuit. The current flow should not exceed the safe limit. Since the fuse wire is thin, has a low melting point and develops high resistance, it prevents the flow of excessive current in the circuit. Thus, we can protect costly equipment from damage due to overload or short circuit. Why should we use porcelain casing? Because porcelain is a non-conductor and withstands high temperatures. There are two types of fuse available. They are the plug-in type and the cartridge type. There is a third type of fuse called MCB, Miniature Circuit Breaker. It breaks the circuit in the event of overload and short circuits. Overload is caused by lack of maintenance, aging of equipment, thermal damage, undercapacity of the power line, excessive usage of appliances, and quality of power. Sometimes we overload the electrical circuit by connecting too many appliances at a single point of wiring. Overload is also caused by switching on all the appliances connected in one section of a cable at the same time. It can also happen if a high-powered appliance is connected to a circuit designed for low-powered gadgets. The causes of short circuit are weakening of insulation, seepage of water, contact of live and neutral wires with each other, bolts or screwdrivers, for example, trapped between the live connections. We can prevent appliances from overload and short circuit by using fuses or circuit breakers suitably. Where should we connect a fuse in the circuit? The fuse is always connected to the live wire. When the fuse blows off, the entire current becomes neutral. If the fuse is connected in the neutral, the circuit remains live even after the fuse melts. This cannot prevent damage to our electrical gadgets, which will still be live. Can we use a single type of fuse for all connections of various current strengths? No. Each fuse has a specific current rating. Let us consider a fuse that can withstand up to 5 ampere of current strength. When the current exceeds this rating, the fuse wire melts and vaporizes with a small explosion. A gap is formed and the currents stop flowing. We say that the fuse has blown. Resistance decreases with the increase of thickness of a conductor. The thicker the fuse wire is, the greater is its capacity. You can find fuses of different current ratings in different sections of domestic wiring. Generally, there are two types of sockets used in domestic and power lines. They are 5 ampere and 15 ampere. Power cables for heaters, fans, TVs and washing machines are connected to 5 amp sockets in domestic lines. Plugs of geyser and air conditioner are connected to 15 amp sockets in power line. We can use the equation shown to select the type of fuse and cable for an electrical appliance.